Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good day to you, Doctor. Today we'll be presenting our lab project, which is the library file management system. So these are the members of our group. Me, myself, Muhammad Syambi bin Muhammad Sareh, and then we have Tengku Nur Afrina, Nur Farha Nadira, and also Nur Arifah Adila. So this is the project management and the team structure. I'll be presenting the introduction, system architecture design, and also the flowchart. Farha Nadira, she will present the reader thread implementation. Tengku will present the writer thread implementation and also the file handling. And Arifah, she will present the synchronization engine and also the testing phase. So basically, the project is about simulating a real library environment where multiple users can access one shared record file at the same time. So the student will act as a reader and the librarian will act as writers. We use the mutex and semaphore as per the instruction because this mechanism can prevent data corruption and during the simultaneous use. Also, we want to ensure data consistency for a safe design that maintains accurate records during simultaneous access. So these are our problem statements. Basically, the current library system always have problem with simultaneous action where they will cause a race condition, file corruption, and then inconsistency, and also the uncontrolled concurrent file access leads to a highly unpredictable system output. This may cause a very big problem. Also, the system permits multiple readers, but they restrict the writers to exclusive access only. So these are our problem statements. So these are our project objective. Basically, we want to design a functional system using concurrent threads. We want to implement the reader and writer synchronization. We want to allow multiple readers, allow multiple writers at the same time. We want to prevent risk conditions and data corruption. We want to maintain consistency of the library records stored in the shared file. Provide execution logs for monitoring system behavior, and also demonstrate a correct synchronization through testing scenarios. So for the overview of the system architecture, first we have the thread manager, which spawn reader and writer threads. We assign the unique identifier and prevent resource leak. And then the reader threads represent the student session. And then the writer threads represent the librarian session, the write logs to modify records one by one, and then the synchronization engine that uses the mutexes and semaphores to protect shared variables and enforce access rules. We have also the file access layer, which handles the low-level input and output operations, and then the logging system, which record log request acquisition and release with precise time. So why do we do this? Is because for the component logic, the threads will map the student and the librarian to simulate the real world resource quotation, and then the shared file act as a central database. The mutex protect shared counter variable to prevent risk condition, like we say in the problem statement, and then the semaphores, the WRT semaphore grants the exclusive access, and then while the Q semaphore ensure fairness for writers. Logging provides a chronological record to verify synchronization and detect logs. For the structural benefits, the clarity, the code is easy to read. Modularity, developers update individual part without changing the entire system structure, which is really good because we save money. And then the correctness, the strict log enforcement prevents data corruption, and also it maintains the database integrity. So for the overview of the system architecture, first we have the thread manager, which spawn reader and writer threads. We assign the unique identifier and prevent resource leak. And then the reader threads represent the student session. And then the writer threads represent the librarian session, the write logs to modify records one by one, and then the synchronization engine that uses the mutexes and semaphores to protect shared variables and enforce access rules. We have also the file access layer, which handles the low-level input and output operations, and then the logging system, which record log request acquisition and release with precise timestamp.
Alright, so in my part, I focuses on the reader thread implementation, which is one of the core components of our library file management system. In our system, the reader represents a student, so whenever a student wants to search for a book or view library records, that action is handled by a reader thread. What's interesting here is that multiple students, meaning multiple reader threads, are actually allowed to access the library file at the same time. They don't block each other because reading doesn't change any data. Now looking at the workflow on the right side of the slide, when a reader enters the system, the first thing it does is join a queue. This queue is important because it ensures fair access, especially when the writers are also waiting. After joining the queue, the reader increases the read count, which is basically a counter tracking how many readers are currently active. Here's a key rule. If this reader happens to be the first one in, it will lock writer access by acquiring what we call the WRT semaphore. This prevents any librarian or writer thread from modifying the file while students are reading. Once done reading, the reader decreases the read count, and if it's the last one out, it releases that writer lock so the writers can proceed. So the whole flow is enter, join queue, increment count, log writers if first, read, decrement count, release log if last, then exit. Now let's look at how this actually works in the code. On the left, we have the reader entry section. The first line, same underscore wait in the bracket and queue, makes the reader wait in the queue before doing anything else. This is what implements the writer priority feature. It ensures that if a writer is already waiting, new readers won't just cut in line. Next, we log the mutex and increment read count. The mutex here is specifically protecting this counter variable because if two readers try to update it at the exact time, at this exact same moment without protection, we get a rest condition. Then we check if read count equals 1, meaning this is the first reader. We call send underscore wait in bracket at NWRT to block any incoming writers. After that, we unlock the mutex and release the queue semaphore so other readers can also enter. On the right side, we have the actual reading section. The code opens our shared file, library.txt, and reads through it line by line using a while loop. Each reader prints out the book records it finds. The important thing to note here is that multiple readers can run this section at the same time. They all reading the same file concurrently, and since no one is writing, there's no conflict. This is what makes the reader-writer model efficient. Finally, let's talk about how a reader exits cleanly. Once a reader is done reading, it needs to properly release its hold on the shared resource. So we lock the mutex again and decrement read count. Then we check if read count equals 0. That means this is the last active reader. So we call same underscore pause in bracket and WRT to signal the WRT semaphore, which wakes up any writer that was waiting. Then we unlock the mutex. This exit logic is just as important as the entry logic because if we don't release the semaphore correctly, the writers will be blocked forever, which is exactly the kind of deadlock we're trying to avoid. So to summarize my section, the reader thread is built around three phases. And three, where it controls access and protects writers from being cut off. Reading, where multiple readers work concurrently on the shared file, and exit, where it properly releases resources so the system keeps running smoothly. The synchronization mechanisms, the mutex, the WRT semaphore, and the queue semaphore all work together to make sure students can read freely, but never at the expense of data integrity. That's the beauty of the reader's writer's solution. Next, we will move to the next presenter.
Assalamualaikum and hello. My name is Tengku Nur Afna Batusha binti Tengku Nasrun, and my part is writer thread implementation and file handling. The writer thread is responsible for modifying the shared resource, which in our project is the library.txt file. Unlike reader threads, writers cannot access the files simultaneously. So, before writing, a writer must obtain exclusive access using semaphores. This prevents race conditions and ensures that the data remains consistent. The overall process is simple. A writer thread enters the queue, waits for permission to write, updates the shared file, records the activity in the log file, updates statistics, and finally releases the synchronization resources so that the other readers or writers can continue. This slide shows the core implementation of the writer thread. First, the writer calls SemWait on the queue semaphore. This places the writer in the synchronization queue and helps prevent starvation. Next, the writer calls SemWait on the write semaphore, also known as WRT, which is write. This guarantees exclusive access to the shared file. While a writer holds this semaphore, no other writer or reader can modify the resource. The file is then opened using OFStream with iOS app mode. The append mode is important because it adds new content to the end of the file without deleting existing books. In this project, each writer adds a new line containing its writer ID. After the writing operation is completed, the writer releases both semaphores using SemPost, allowing other threads to continue execution safely. For file handling, our shared resource is library.txt. Initially, the file contains a list of books, which is the operating systems, database, enterprise network and wireless technologies, etc. So when a writer thread executes, it opens the file in append mode and adds a new book entry at the end of the file. Using append mode ensures that existing data is preserved and no information is lost. The synchronization mechanism protects this file from concurrent modifications. Without synchronization, multiple writers could write at the same time, causing corrupted or inconsistent data. Therefore, file handling and synchronization work together to ensure safe and reliable updates to the shared resource. Besides writing to the file, the writer thread also contributes to logging and system monitoring. Before and after writing, the writer records messages into execution log. These logs provide evidence that synchronization is functioning correctly and help during testing and debugging. The writer also increments the total writes counter. At the end of program execution, this statistic is displayed together with the total number of reads. Overall, the writer module contributes directly to several rubric components, including thread implementation, file access, synchronization correctness, logging, and testing validation. This demonstrates that writer threads can safely modify a shared resource while maintaining data integrity in a concurrent environment. That's all from me. Thank you.
Now let's break down the precise operating system mechanics of our fourth test scenario. In scenario 1, we deployed 5 readers threads with 0 readers. Mechanically, the first reader locks the internal mutex, increments our read counter, and drops the write semaphore to 0. Because subsequent readers see that the read counter is active, they bypass the write log entirely. This allows all readers to exist inside the critical section at the exact same time, confirming true parallel database reads. In scenario 2, we isolated 3 writer threads. Here, the first writer drops the write semaphore to 0 and opens the file in append mode. While it is writing through this, the Linux kernel transitions the other incoming writers from a running state to a block state, placing them into a sleep queue. They only execute sequentially, one after the other, proving strict mutual exclusions. Scenario 3 simulates a realistic mixed environment where readers and writers fire simultaneously. Our logs showed that active reader successfully blocks a writer. However, because of our algorithm use a reader performance model, incoming readers can continue to join the critical sections while the writer waits in the queue. The writer is only unblocked when the very last active reader exists and drops the counter to 0. Finally, scenario 4 is our high-load stress test in the 30 concurrent threads. This scenario forces the Linux OS threads scheduled to rapidly swap contexts, creating heavy contentions of our logs. Despite the sudden traffic spike, the system safely attributes every request, completes all tasks without freezing, and proves that our architecture is completely free of deadlocks. Moving into section 6, we evaluated the architectural performance and real-world efficiency of our system. Our analysis confirmed that the reader path is highly optimized. It completely eliminates bottlenecks by allowing simultaneous non-blocking file access. Conversely, the Writer paths sacrifice concurrently for safety, strictly serializing while request to guarantee absolute data integrity. To monitor this behavior, we implemented a real-time logging subsystem. While capturing these microsecond accurate trace logs introduce minor disk I/O latency, this trade-off is highly justified because it proves an immutable, transparent audit trail of our thread states. Next, we candidly address the systemic limitations of our current design. Because our project implements a first reader-writer problem model, it inherently favors readers. This means under heavy, continuous student read traffic, our library and writer threads face a severe risk of starvation, sitting in the semaphore queue indefinitely. Furthermore, because thread must constantly open, append, and close physical file on the desk, our system performance is fundamentally I/O bound. The ultimate execution throughput is restricted by storage read-write speeds rather than the raw processing power of the CPU. Finally, the most valuable engineering takeaway during our integration phase was watching a critical synchronization bug in our reader module. Initially, we noticed that our global tracking counter was occasionally displaying incorrect totals under high load. Upon a deep code review, we discovered a race condition. The variable increment was executing just outside our protected mutex critical sections. If two reader threads switch contexts at the exact microseconds, they corrupted the count. We resolved this by refactoring our source code and pulling the increments safely inside the mutex loop, ensuring complete variable isolation and mathematical accuracy.
In conclusion, our group project successfully implemented a library file management system using the readers-writers synchronization model. The system allowed multiple readers to access records simultaneously while ensuring writers had exclusive access when updating the shared file. By using mutexes and semaphores, we prevented race conditions, deadlocks, and data corruptions. The writer priority mechanisms also improved fairness by preventing writer starvation. Overall, the project gave us valuable hands-on experience in applying operating system concepts to solve real-world synchronization problems. That's all from us. Thank you.